Welcome to mesh analysis using KVL and KCL, problem number 5. We are going to do a slightly more complicated problem than we've done before. We have 4 resistors, we have 3 current sources, and 3 DC voltage sources. So start the problem as normal, which is pick a mesh. I've decided to start in the top left mesh section. And going clockwise around this subsection, I'm tracing a current path. As I enter the resistive components, I place a plus, and as the current exits, a minus. For the current source, you might have noticed I placed a plus as I encountered it. That's because the current is going up. For current sources, where current is exiting the current source, the polarity is positive. Where current is entering, it is minus. So that is why the polarity of the current source is the way it is. And of course, the DC voltage sources, we already know what the polarity and the voltage is across those. So I'm going one mesh at a time. I'm not worrying about what the other meshes are doing. Each mesh current has its own orientation, independent of the others. And it doesn't really matter which way you decide to go as long as you are consistent with how you label the polarity. So I3 on the bottom left-hand mesh. Once again, I'm going clockwise around the subsection. And that is I3, and this one will be I4. Now I4 will give us a 4 amp current from the 4 amp current source. The mesh subsection current will take on that 4 amps. You'll see that shortly. Now we can start writing out the loop equations, starting from the dot on the first submesh. We have minus 5 as we trace clockwise. We trace a loop around this subsection. As we hit the current source, we don't know the voltage across this. We know the current is 3 amps. We don't know what the voltage drop is, though. We will calculate this. This will be calculated. And we have those 2 current sources in that subsection. For loop 2, once again, starting at the bottom left-hand corner and going clockwise, we simply trace a current path around this subsection. We have 25 I2 minus I4. So take note of that. From the reference frame of that mesh, for the current I2, the I4 current is going against it through the 25 ohm resistor. So that's why you have the 25 ohms times I2 minus I4. Now for the third subsection of the circuit, once again, tracing clockwise, get this equation. And again, it's going to be 15I3 minus I4 for exactly the same reasons that were just discussed. And the loop 4 equation is here. So we have quite a mess here with just 4 equations and 7 unknowns, well, seemingly 7 unknown variables, I1, I2, I3, I4, and the voltage drops across those 3 current sources are all unknown. So we need some relationship within the circuit in order to eliminate some of these unknowns. Ideally, we'd like 4 or less unknowns with our 4 equations. And that way the circuit would be solvable. So I've denoted an N for north and W for west. These are nodes on the circuit diagram. At node N, we have 3 amps entering it from the bottom, and we have I2 exiting it from the top and I1 entering it from the left side. And that gives us a relationship. I1 is equal to I2 minus 3. And from the node on the west section, we have 2 amps entering it from the right. I3 comes up through the bottom, and I1 exits through the top. So this gives us another relationship that we can use, and it helps to find a solution for this system of equations. So this is something you typically have to do for a problem like this, is find some relationship between the current and voltage sources. So here the equations are just being simplified with a little substitution of those relationships that we found. I1 is equal to I2 minus 3. Just plugging that back into the loop 1 equation, and we're reducing the complexity a little bit, making it a little bit neater. Likewise with loop 2. I4, we simply know that's 4 amps. Can read it right off the diagram. So that's easy. Loop 3, we have a couple things going on. I4 is equal to 4 amps. We can also use the relationship that I3 is equal to I2 minus 5. So we've expressed both I3 and I1 in terms of I2, and that helps quite a bit. And loop 4 is a little bit larger. I'll just write what it reduces to. 235 minus 40 I2, which is equal to the voltage drop across I4. So we can start adding some of these equations together to get rid of variables. There's nothing too complicated going on here. I'm just looking for opportunities of where I can eliminate some variables. Here we're eliminating the voltage drop across I3 from the loop 1 equation and the loop 2 equation. So adding those two together, we get this expression minus the voltage drop across the I2 current source plus 40 I2 is equal to 125, and then adding that to the loop 3 equation. And we can solve for I2, which comes out to 4.6 amps. So I2 is 4.6 amps. From this result, it's not too hard to plug this value into other loop equations or current node equations to solve for those values as well. I3 is equal to I2 minus 5, which gives us I3 as minus 0.4 amps, 400 milliamps, going in the opposite direction. So the actual I3 current is flowing in the opposite direction than we've denoted on the diagram. I1 is 1.6, and the voltage drop across the 4 amp current source is going to be 51 volts. And we can solve for the other voltage drops across the remaining current sources using the loop equations. We have a 59-volt drop across the 2-amp current source. And we can find the voltage drop across the 3-amp current source using the loop 2 equation and plugging in the value for I2. Which gives 48 volts. So there's a 48 voltage drop across this current source here. And checking this result against the simulation is pretty similar. A minus 51 volts across I4 on the bottom right. You can see that. Again, this is with respect to ground. The currents seem to match up with the results that we have solved for. Was a little tricky. I do admit it did take a couple times to get this correct. I spent a little too much time on this, to be honest. So these mesh problems can get pretty tricky. If you keep adding mesh subsections, they can certainly increase in complexity. Anyway, thanks for watching. If you'd like to try problem number 6, we'll see you in the next video.